So good afternoon, everyone, and thank you for joining this. I'm happy to have you all here in this afternoon. You're half sleepy, half awake, right? So I'll talk about XAI. What is XAI? Like this lady there was asking me, what is XAI? XAI is the short form for explainable AI. I'm not an expert with AI or even explainable AI. I know a little bit about knowledge graphs and my background. I'll give you a quick background about myself. I work as a technical solutions director at a company called OntoText. OntoText is a company that builds a graph database. It's called GraphDB. GraphDB. It's a special type of a graph database called RDF graphs, and we'll see about that. I also, on the side, has been doing a lot of independent consulting. I do independent consulting in data engineering, data ops, stream processing. This lady from Texas A&M was talking about stream processing today. So I do a lot of work with Spark, Kafka. I've written a book on SQL engines. I've also developed an online course on how to work with big data about 5-7 years back. I was also an ex-Gartner analyst. I worked with Gartner as an analyst for about 4.5, 5 years, talking to a lot of CTOs, CDOs, advising enterprise architects about building data architectures and data solutions.
Sorry.
So we need to set.
Can you switch the view to mirror?
Change whatever you want. Yeah. Very good.
I actually don't know how to do it.
Not full screen.
There's a button, but they changed the layout.
You have to do what?
So we want to, when you are sharing screen, oh, you are sharing this screen, not the other screen.
Oh, is it? Okay. But here it's showing this, right? But there it's showing that.
Okay, so let me try.
I see. Okay. We can just hold on.
Yeah.
Maybe go here.
This one.
And then click share. Yeah.
You got it? Cool.
Yeah.
Cool.
Okay, good. So they're trying to. I was seeing a different screen. The Zoom was seeing a different screen. Okay. So okay, let's get started. Enough of talking about myself. So this is what we'll try to cover. What is a graph? What is a knowledge graph? Why do we need knowledge graphs and explainability with knowledge graphs, right? So before I start, let me ask you a question, or let's start with a small quiz, right? Take any celebrity you know in the world, right? And take any other remote person who is on the planet, right? Remote on an island. How many connections do you think they need to get connected? Any guess? Very close, right? We have this famous book called 6 Degrees of Connection, right? It's very hard to imagine, right? Of a planet with 8 billion people, you just need 6 connections, right? And this is a famous, well-known documentary on Netflix. We are all connected together, right? When like financial organizations, health organizations do this patient 360 or, customer 360, they call know your customer, right? Which I call as kill your customer, because they ask so many questions, you have to give so many documents, right? So that's what they're using. They're using all these different data sources to build a picture about you, to build a 360-degree view about you, right? And this is all about graphs, right? Graphs help you to connect, because the biggest advantage of graphs is it helps you to think in a very connected way. We are all connected. And this is a famous incident which made graphs very popular. I don't know how many of you know about it. It's called Panama Papers, where a bunch of journalists in 2016, they figured out how the wealthy people were doing money laundering, trying to put it into getting money across from different, third world countries or rich countries into neutral countries, and how they were siphoning the data. They got this by analyzing a lot of textual data and build a graph around it. And that's what made Neo4j, the biggest graph database, the most common graph database, very famous, right? And today, if you look at it, right, graphs are everywhere. So graphs are everywhere. We're using graphs every day. We just don't realize, right? The moment you're using GPS, you're using a graph. The roads, the intersection of the roads are the nodes, right? And the roads themselves are the connections. When you're walking in your house, right? When you're moving in your house from one room to the other, your brain internally is using graphs. All of social media is basically a graph, right? During COVID times, when we are having these supply chain problems, supply chain is all about graphs, connecting the suppliers with the with the producers, right? So graphs are all around us. We are using it every day. And same with knowledge graphs, right? And I'll tell you what's the difference between knowledge graphs and graphs. But knowledge graphs are built on top of graphs, right? And knowledge graphs, we are also using knowledge graphs every day. The moment you use a search engine like Bing or Microsoft's Satori engine, or even Google, right? You get a panel on the right-hand side, which talks more about your search. And Google in 2012, they changed their architecture of search from going from an inverted way of search, using inverted indexes, they went into their own knowledge graphs, where knowledge graphs was basically the word coined by Google, and it became very famous from 2012 onwards. When if you search, for example, dentist in Google, you will also get, or any other search engine, you typically will also get things about orthodontists, right? How does Google know that dentists and orthodontists are related? Because there is a knowledge graph behind it. There is an ontology, there is a taxonomy behind it, right? So graphs are everywhere. And there are two different types of graphs. And I'm giving you this background to help you understand how knowledge graphs can be used for XAI, right? So what is an LPG? It's not liquefied petroleum gas, it's labeled property graph, right? Labeled property graph is, again, very simple to conceptualize. Think about LinkedIn, right? You are a person, you are connected to another person. This person has a set of attributes, right? Their skills, their qualifications, and the way they are connected, the connection itself has attributes as well. The day they were connected, how they got connected, right? How many interactions they're doing. So these are all attributes. So that's how you build a labeled property graph, right? Which is very intuitive, right? And that's the reason why, even though we all use relational databases to a lot of people today have become oxymorons, because it really does not capture relations very well, right? For those of you who have done data modeling, right? When you have end-to-end relationships, right? You cannot model that in a relational database easily. You have to build another middle table that has the mapping. And that middle table has no meaning in real life. You're doing it because relational databases cannot handle it. And that's why graphs are very elegant. It helps you to model the way you think is the most biggest gain about graph databases. It's very intuitive, right? And this is the example from this company that I worked for with Ontotex, right? Is an example of an LPG. If you take a pizza, right, and you take it as an object, right, it has different things. It is made up of dough, it has olive oil, it has mozzarella, and each of these has their own attributes. So that's how you model an LPG. And that's one of the reasons why Neo4j became very popular. When you talk about graph databases, a lot of people say Neo4j. They go and download Neo4j because it's very easy to get started with. That's LPG. But LPG has certain very good qualities and certain things that it cannot do well. And that's where comes what we called RDF graphs. RDF graphs is a resource description framework. And there is a difference, very fundamental difference between RDF and LPG. And that's what makes RDFs very suitable for knowledge graphs. So what is it? And that's a fundamental. If you understand that part, a lot of things will make sense, which is an RDF, unlike a LPG graph, RDF breaks facts into very most granular part. RDF is actually subject, object, triple, and how they are connected. Subject, predicate, and object. That's the most minimal it can have. Each of these nodes cannot have any attribute. Any attribute you have needs to be modeled as another node. So that's how you see here. A person lives in a city, right? So lives in is this part. This lives in is a resource. City is a resource, and person is a resource. Any attribute of that person is also a resource. It's not attached to the person itself as an attribute. Because now you can model this in its most granular form, that's where it gets power. Now, any LPG can be converted into an RDF graph. They are sort of isomorphic. You can convert one to the other. But an LPG graph can represent a lot more information in a more concise way compared to an RDF, because RDF becomes very big. So typically LPG graphs, when you go to GPS and tell it to find out the route from point A to point B, it uses an LPG graph, because LPG graphs are very useful in modeling graph algorithms, right? When UPS comes and delivers to you, right, different packages, their optimization algorithm in terms of the route they're going to take sort of uses traveling salesman's problem in some ways, and it is modeled as a graph, as an LPG graph, not as an RDF graph. So LPG graphs are very useful when you're modeling algorithms, when you're doing these traversal algorithms. You have to go from one node to another to find out the path. RDFs, you can do the same thing, but RDF graphs are very big because you are modeling an RDF graph in a very, very granular way. And this is the most fundamental thing when you go into a knowledge graph, because you are modeling it into its most granular format. You can help it to do reasoning. So there is this thing, reasoning, right? Every man is a mortal. Socrates is a man. So then the next inference is Socrates is mortal, right? We can quickly deduce it. If you model that with a knowledge graph will be able to deduce the fact, that third statement, that Socrates is mortal, because it has modeled it in the most fundamental way, at the most granular way. And this is, you see the example of the same pizza here with RDF. It just balloons up because now you have everything modeled as a node and a connection. So that's the most fundamental thing to understand. So what is knowledge graph, right? Knowledge graph typically, again, if you talk to Neo4j will say we also build knowledge graphs, but their knowledge graphs have challenges. They cannot do this inferencing. And this inferencing and reasoning is what helps a knowledge graph in the explainability part of algorithms. Right? So knowledge graph is built on top of concepts, right? And I'll show you an example that will clarify it. Maybe I can go there first. Knowledge graph is built on top. So knowledge graph is built on top of graph databases. It needs a graph databases to store all your facts, to store all your information. And then what it needs are the two most important things, ontologies and taxonomies. That makes it very domain specific. There are thousands of public taxonomy. We always have a taxonomy. We have always been using taxonomy, right? When you classify, let's say, and the animals, right? Classify animals or classify products, right? You have shoes or you have clothing. This clothing is part of this part of the clothing. You have this whole hierarchy, the concept hierarchy. That is the ontology or the taxonomy. Domain experts in healthcare domain, right? In insurance domain, they have their own ontologies. Those ontologies are, think of ontologies as a schema for the graph. Just like a relational database has a schema, right? An ontology is the schema. The taxonomy is the hierarchy. For those of you who have done object-oriented programming, right? You have classes, you have subclasses, you have superclasses, right? A person, a man is a subclass, a woman is another subclass, a child is a subclass again, right? So those things, those information, those domain information, when they are put on top of your data, that is when you get a knowledge graph that gives inherent semantics to it. And the other advantage of knowledge graphs is knowledge graphs can work across not just structured or semi-structured data. When I say semi-structured, it's JSON or XML data, but they can also work with unstructured data. Lot of precision medicine, drug discovery. This company, Ontotext, I work for, they are very heavy in the life science, because one of the major reasons is a lot of life science drug discovery is based on, a lot of papers, literature, PDF documents, and they can do a lot of text analysis on top of it, identify the entities and how these entities are linked together, and how for example, the chemical industry relies a lot when you do pharmaceutical companies, when they use different sort of chemicals and medications, they use graphs to understand these dependency on the chemicals, that this chemical has these elements, this element can affect this, or this compound can affect this. Those dependencies are modeled as graphs because it's much more intuitive, much more powerful. So again, knowledge graphs, as I said, they are used in these search engines, and that gives you the semantics. The way Google gets orthodontists from a dentist search is because it has that ontology to know that orthodontist is a subclass of dentist, and it could be relevant for this search person. You may have heard about, Alexa, Watson. They were all using knowledge graphs in the backend, because Alexa, if you ask it for weather data, right, it will get your location data, it will get your weather data. It has to get that data, and then it merges it together to give you the answers. And knowledge graphs are very powerful when you have to work with different data sets, heterogeneous data sets, and then make sense out of it. When you do customer 360, patient 360, you're getting data from multiple places, patient notes, any other data that you get, right? So you can think of knowledge graphs as plain graphs as well, because they're built on top of graph databases. They can do graph algorithms. But again, if you want to do graph algorithms, an LPG graph is the best way to do it. If you want to do inferencing and reasoning, a knowledge graph that is based on RDF is very important. And knowledge graphs can help you to do not just inductive reasoning. You know what is inductive reasoning is, right? Induction, we all used it in maths, right? Go from a general fact to more specific facts. Knowledge graphs can also do deductive or abductive reasoning. Abductive reasoning meaning you don't have all the information. You don't have all the information, but still can you get to some inference? Because the advantage of knowledge graphs is it knows the taxonomy and the ontology. And maybe if I show a picture, that will become clear. So knowledge graphs gives you that semantics and the context of it. And that's where, we talked about Chat GPT and LLMs, right? This is where LLMs and knowledge graphs are trying to collaborate, where LLMs, a lot of times, they lack the overall context. They have the context of closeness of the words, right? When LLMs were developed, right? When LLMs were developed, they are looking at what the attention window, right? When they built with attention windows and transformers, the attention window is what are the word dependencies. If you look at a text, right? If you look at a paragraph of text, you can model that as a graph. This word comes after this word precedes this. And then if there are multiple words, you can create graphs around this, right? And you can use, this lady is a graph neural network expert here. You can apply graph neural networks on top of it. So you can do these kind of semantic analysis and provide context with knowledge graphs. This goes into how you build knowledge graphs, right? You can build knowledge graphs, as I said, with structured, unstructured data, with different sort of contents, extract. You need a schema mapping. What element of the data is mapping to what element of your graph model? And then you extract it, you apply the ontologies. Each industry, each domain has its own terminology, which we call vocabularies, right? Which only the domain experts understand. You apply all that and you build it into the knowledge graph. And then you can use the knowledge graph to generate more semantically meaningful comprehensions or whatever type, if you want to do summarizations or recommendations. And that's where LLMs and knowledge graphs can collaborate. LLMs often lack the context, which can be provided by knowledge graphs. And this is a typical stack of when you build a knowledge graph is not like a database that you get it, you put the data into it and extract. You do the data integration, you put the data into the graph database layer, and then you have the semantic layer where you are bringing in your own domain ontologies, your own domain taxonomies. And then there is this reasoning, the same kind of reasoning where Socrates is a man, every man is a mortal, Socrates is going to be mortal. It builds these kind of dependencies from the graph and quickly infer newer facts. And then you have a query layer and can build semantic applications on top of it, right? This is, again, going into more details in terms of how you build knowledge graphs and the graph generation process. Typically, knowledge graphs, you use this language called Sparkle. Sparkle is a lot like SQL, but then you have to give it the semantics that you're using to get the queries. So these are the main components you use when you build knowledge graphs. And you think of knowledge graphs as your instance data, that is your raw data. overlay the taxonomy and ontology on top of it, and you will get our knowledge graph. Now, think about this example, right? Cow, we all know this. Cow eats grass, cow does not eat meat, and dog eats meat and dog doesn't eat that. Now, on top of this, what is this ontology and taxonomy I'm talking about? On top of this, we already know, our mind inherently knows that yes, dog is an animal, cow is an animal. And that part is the ontology, the top part of it, right? Every living being has this categorization of animals and plants. Once you put that on top of that data, right? A lot of things become much more clearer to us. So the advantage of knowledge graph is, again, as I was saying, you model each of these things in its most fundamental granularity. And each of these things eats or is a type of, or has, let's say, body parts, right? Has a hand, has legs, has a tail, has a head. All these relationships, right? These relationships are very standardized. You cannot create, these are all available. These are all available, you just import it. Just like when you write code, right? You import certain libraries. You import, when you write an LLM code, let's say you're writing LLM index-based code. You're importing the LLM library or LLM index library. Similarly, you can import these well-defined granular concepts into your knowledge graph. So what happens is, yes.
Well, sorry, do you want questions at the end or?
No, keep going. Let's ask.
So just one question is for the edges. I mean, how do you have to feed it the list of is and eats, or like how do you generate that?
Yes, that's a good question. And certain knowledge graph engines have that capability to understand that this is a part of this. They have that knowledge. So the ontology will tell you that. The ontology will tell you certain of these edges will be part of the ontology. Like animals is a living being, plants is a living, that's well known. That's part of an ontology, so that's known. But then this connection that dog is an animal, right? Cow is an animal. It is part of another ontology that's well defined somewhere, right? And when you import it into the knowledge graph, and each of these things has a unique resource identifier, means it's unique around all your data sources, or around globally all the data sources. So there is only one is a type of relation. That makes this very machine readable. Machines can then interpret it, and that's where the reasoning becomes much more possible.
So I have one more question. Maybe this just, I know this is a toy example, but all those are binary. Is it possible, like, is there or could there be an edge between animals and plants? Because sometimes sometimes animals do eat plants and sometimes they don't. So would it not get an edge?
No, we are not modeling the eating part here. We are just classifying the cow and the dog part here with the animals and the plants and the grass here.
Okay.
Right? But yes, a dog eating or a cow eating a grass, and we know the grass is a subclass of a plant. So that subclass, superclass mechanism is embedded within the ontology. Okay? And that ontology, if you go out and search for ontologies, there are well-defined ontologies out there in each of the domains. In the healthcare domain, in the insurance industry domain, there are a lot of ontologies. And each of these ontologies is by itself a knowledge graph. And each of these links, right, has a unique identifier. There is only one of that. If you click it, you will get to a website which will say, URI, right? It's not University of Rhode Island. It's URI is Unified Resource Identifier, right? Which means that there is only one instance of it, which removes ambiguities. Yes, Alex, you had a question.
Yeah, good question. I mean, I'm listening to you, and this reminds me of actually, can machine learning be applied on this graph? Because there is a field of graph machine learning.
Correct.
And this is very similar to that.
Absolutely.
Graph neural network.
Absolutely. This lady there is a graph machine learning expert. She's doing a PhD here, right? Under a professor.
You must be familiar with the work that Yuri Leskovich is working in this space.
Who?
Yuri Leskovich, the Stanford professor.
I can't recall his name right now, but maybe I can talk to you about that. I can get his name and but yes, graph machine learning, knowledge graphs were very hot topics before ChatGPT came and wiped it out, right?
Right.
This decade was supposed to be knowledge graph, and that's why I joined this company.
This is more powerful.
Exactly. If you look deeper into this knowledge graph part, you will realize the value of it because everything is standardized. There is only one is a relation, and that means that now you can model your elements in a way that is interpretable, and that's where I think its applicability to explainability becomes important, right? And I'll show you an example later on. We can skip this slide. It's showing how how knowledge graphs become useful. I don't know what's the time.
4:15.
Okay, 5-7 minutes more, and then we'll wrap it up.
Well, we have till 4:40, right?
Oh, is it 4:40? How long is it?
Oh, no.
No, you're
Sorry,
right.
my schedule.
Next talk is
We'll keep it to 4:30.
4:20.
We got 40.
Okay.
Which means we will end at 3.
Maybe 5 minutes.
Yeah.
Another 5 minutes? Okay. So this is what explainable AI is, right? And again, I'm not an explainable AI, expert by any means. And this area of explainable AI with knowledge graphs is very interesting. There is no yet standardized way of doing it. It is still evolving. There's a lot of research going on, lot of ways techniques going on. And I'll show you an example, right? The reason why do we need XAI, right? It's because most deep learning are just like black boxes, right? We're getting the answers through the softmax or the activation layer, and we're just getting the probabilities. We're not understanding why we are getting it, right? And these are the characteristics. XAI, we know why we need it, regulations, industry, and all that, right? And XAI is done in different ways here, right? In different ways where, you are, but with XAI, with current XAI, you don't understand what's happening in that hidden layer of your DL, right? Of your deep learning stack. You just know what is it on the outputs, not in the inside. Those are some of the areas where, and this is where, we have heard about word embeddings, right? And there is a similar concept in graphs. It's called graph embedding, where you are representing graphs with random walks, right? You let loose an agent, it does a random graph walk from one edge to the other, and it encodes it as an embedding. And graph embeddings have a lot of value to quickly figure out similarities. Just like vector databases do today, graph embeddings can do a similar kind of a thing, right? So knowledge graphs in XAI, with embeddings, they can provide you a lot of semantic meaning because you're creating embeddings, and word embeddings and graph embeddings can give you meaning. It's one of the steps closer to helping you understand. So knowledge graphs, because they are machine readable, they are very machine interpretable. Machine readable makes it machine interpretable as well as the next step. You can use it as for doing, symbolic AI kind of things, which is very essential for one of the essential things for doing explainable AI, right? And you can apply knowledge graphs for explanation either in the pre-modeling stage, which is only very data centric, which is nothing to do with the model. You can do it while you're doing the modeling, or you can do it at the output layer. Right, I'll quickly go through all this, but I'll show you one picture here, which probably will help you. I'll skip through. There are challenges with knowledge graphs. Knowledge graphs, a lot of people don't know, is because there is a pretty steep learning curve with knowledge graphs. But once you learn knowledge graphs, you will see the value of it, where that power comes from. As I tried to give you some idea of these machine readable capabilities. Right. The challenges of knowledge graphs are also around refreshing, just like ChatGPT. It's still 2021 data, September 2021 data. Knowledge graphs, you have to continuously refresh to make them explainable. And this is how in deep learning, you could apply knowledge graphs at each of the layers. You take the input data and apply the ontologies and knowledge graphs to infer better quality results at each of the layers, if you apply knowledge matching to understand what are the concepts, what are the entities that are going into each of these, you could have some amount of explanation. And I'll again show you an example. There are different ways. So there is this way to generate embeddings. It's called RDF to vector, right? We have word to vector. We have so many two vector products now. RDF to vector will generate a vector from your RDF graph data. And then you can apply LIME. We all know LIME in terms of its explainability with certain machine learning algorithms. You can apply LIME for RDF to vector. There is an open source utility available to do that, to use on RDF LIME to get certain explanations. And there is this very powerful knowledge graph called concept. There are a lot of these knowledge graphs that are freely available that you can import to a graph database like GraphDB. And ConceptNet is one of them. And I'll show you like, for example, if you have a picture like this, right? If you have a picture, just focus on the picture. If you have a picture on this with image segmentation and image classification, you can figure out what are the components, right? You can just understand what are the components, but you won't get the arrows, right? That these are, you'll just know there is a hat, there is a lady there is a plate, there is food, this is the color, right? And then when you put on top of it the knowledge graph, right? That the food could be veggies, it could be thing. There is a color associated with it. Once you start put knowledge graph on top of this, these arrows get filled out, these arrows get populated, and then you can interpret that, yes, this is probably showing you a chef. And what is the reason for it? You can understand because it is showing you these components, and these components are all part of this picture, and they're also dependent upon one another. So
it's learning from the previous structures like this?
It is learning from an ontology like this, which is already available in this ConceptNet.
And you created those ontologies?
No, those ontologies are freely available, and you can import them into your graph database.
Okay, but if you have something completely new, you have to create these.
Correct. If you have something new, which is domain specific, yes, you have to create it. Perfect. So that's how is one way of doing explainability with knowledge graphs. Explainability with knowledge graphs is a very new field. Lot of work is going on. No established pattern. Like CAP and LIME are still sort of established patterns in other machine learning, plain machine learning algorithms. In knowledge graph, with XAI, with knowledge graph, we still don't have. There is a lot of work going on. I think I'll stop here with that. There's nothing much to add, but there are certain references here which you can look at in terms of, I'll send you out if you're interested. But that's in short about it. It's a difficult topic. It's a difficult area, both knowledge graphs and XAI. But yeah. Thank you. Thank you for listening. Yeah.
Problem. I'm the last person standing in the
Not the least.
Yeah. They will not be cultured.
Yes.
Excuse me, line is about this one. Yeah.
Here, yeah, and share screen. Where is your slide?
That's the goal.
This.
They're visible?
Yeah, it's
Oh, good.
right. You can forward this.
Yes.
Slides, yeah.
Thank you. Good evening, everyone. I'll make it quick. I don't want to be a big hurdle between you and your drink. Okay. My name is Prabhu Ramakrishnan. I'm a principal data engineer at CVS Health. I work on various technologies and I build data production framework for CVS Health, especially in Hadoop 3.5. And like when we put GCP foundation, I was the one it's laying down the architecture for it. Next one is some disclaimer. It's required by my legal team. I'm CVS employee, but whatever the views I'm sharing here, everything is my personal. Okay. So don't quote me and don't sue my company. Okay. Before I want to start about it, I want to give a brief history about it. Hey, what we are doing today is, and I want to give the reason of why we are doing. If you take the healthcare industry, it was it's a kind of a wild west. Like you can share the data any way you want in before 1996. Okay, even your employer has access to all your health information. He or she can decide whether he needs to provide a promotion for you or not based upon your health information. Whether you got a diabetes or do you have some ADD or those kind of thing. Look at your health information and they can make a decision on your future career goal. In 1996, the HIPAA got introduced, but it's introduced not with intent of securing the data. It's more in the intent of sharing the data in certain way, not exposing much of your personal information. When they started, at the time your date of birth is not a protected information, health information. Wherever they share, they just strip off your name and address, share the data along with your gender, date of birth, and zip code, everything for analysis and it's reducing waste, fraud, and abuse analysis, those kind of a thing. That's how I started. But pretty soon, when they started sharing the data, there was a big news happened. Happened in it's in mass at the time. Massachusetts state government employees' data got shared in publicly to go and use it for it's a better use of to identify the effectiveness of the program. Okay. And once the data is out, it's one of the MIT student, Dr. Sweeney, at the time she was a student, she got the data. And what she did was she then pulled the Cambridge Mass voters data too and put together. Okay. So pretty soon, how she can able to navigate to the governor at the time, the governor William Weld, a governor, personal information. How did she reach out that? First, she eliminated all the people who are less than 18 in the given zip code. Then she matched all those adults recorded. Then she identified the gender specific unique data set that is reduces further narrowed down the data. Then she went up to the date of birth and the unique person, the male gender, easily she could able to identify the governor and she could able to list down all this data about what is his health condition and all those things. And it's become a big news at the time. Okay, this led into further restricting the sharing of the healthcare information. Okay. What had happened then, it's HIPAA privacy rule, it got much stricter, especially in the 2003, there were much enhancement happened. that's the reason, like it's a you, whatever the form you are seeing, if whenever you go to your health provider, they'll be giving a form, HIPAA form, and ask you to sign by saying that, like, hey, the rule says the each and every patient should aware that the data can be shared for the treatment, payment process, and operation perspective. Okay, so they need to get a consent. The provider need to get a consent before even sharing the data for any further use. Okay, and further, like it's in 2005, the first time they have introduced standard for electronic records. Till like 2009, if you go to any doctor's office, you can see the like file cabinet full of with a file folder, yellow color folder, like with all your record, bunch of those things. Then whenever you doctor wants to see that, the nurse she will come with 1 kilo of or a couple of pound of paper belonging all health in history of yours. Okay, the first time in 2005, they came up with a recommendation for electronic health record or like electronic personal health information. Okay, until 2009, there were no governance. There is no enforcement agency on how are you using the people's health information, protected health information, all those things. In 2009 only, it came under to the like the Health and Human Services Office. What had happened at the time, 2009, the Health and Human Service took in charge of that, and they start incentivize the people who are implementing this policies, HIPAA policies, and securing the data properly. Okay. In further down, like it's when technology evolves, like it's we started sharing the data in a left and right. Before 2009, like we used to share our data in a plain text, in a plain FTP. If anybody like is having like a spoofing inside the network, they can go and get all those information without even anyone's consent. Then only like there were stricter restriction on like, hey, you need to transfer this data over like it's an encrypted form, otherwise like it's SSL layer. In 2013, like it's a further restriction happened, and it's dictated how you need to secure your data and for what you can use the PHI data and how you have to de-identify data. All those restriction specification has been mentioned in the 2013 version, and they have a timeline to up to 2015 to implement all those recommendations. As part of it, like they want to implement ICD-10. Before that, ICD-9, which does not cover all the diseases like modern diseases or like whatever the advantages happened during that time. So this is a brief history, like it's a why we are treating the health information very securely. It's not only our personal interest, and also like it's a government mandate that we have to follow these guidelines and rules. When it's come to the analytics, like it's a why we are very strict about privacy and anonymization in analytic and IT development field, because like the HIPAA mandate that the data can be viewed and processed only for three kind of a thing. One is the treatment, another one is a payment, and third one is the operation kind of a thing. Treatment, any health service provider, the nurse, doctor, or like some nurse assistant, anyone can come and take the look at the data while treating you or helping you. That's the one. Second one is the payment, like it's a billing provider, bill provider. If you have any dispute in your amount, at the time they can look at the data. And also like your health savings account and the flexible savings account, those are the things. The operation things, like whichever, like the computer operation, like the claim processing, another thing. That's what. But our analytics, IT development, anything does not come under any of these three categories. That's the reason we have to decrypt the data. Sorry, de-identify the data. When it comes to the HIPAA anonymization standard, like it's a HIPAA recommends, hey, there is a two-way, like a major way you can de-identify the data. One is an expert determination, where like you can apply any statistical or mathematical approach and go and de-identify the data. One of the example is a K anonymity is the one like the which falls under like it's expert determination model. The next one is a safe harbor, which is much more stricter and mostly used in many of this organization, health service provider organization, like it's a CVS Health, like USG. I'm not sure about USG, but like CVS Health is very strict about it, and we are using it. What the safe harbor mandate is, whenever you are sharing the data or using the data, the PHA data, you have to strip off 18 different kind of elements from the data. And you have to substitute that. You can substitute those elements by something different than that. When you talk about it, like it's some name, your address, geographical information, street, town number, state, all those things need to be removed. And when it comes to your zip code, we cannot use all 5 digits of the zip code, only like it's the first 3 digits of the zip code can be used. Even when you are using the first 3 digits of the zip code, there is a mandate that like if the total population for the 3 digits of the zip code less than 20,000, you have to go and assign them 000 zip code. So everybody will be put into the common bucket. The second one is like comes to the date. You cannot use the date of birth, service date, date of death, all those element as is. When it's come to the date of birth, you can use an age. You have to strip off like the month and date, but you can use the year as is. And service date and all those things like the same kind of a thing. With respect to comes to the age, if the patient is above 89, we cannot use them date of birth. We have to put them in a common bucket called as like the 89 plus. The next one is like we cannot use the telephone, email address, and SSN for obvious reason. When it comes to like other unique identifier, like MRN number, account number, member ID, all those things we should not use, because if I know your member ID, I can easily go and match with like my plain text data and find out who you are and like what is your condition is. That's a restriction. Okay. Let's talk about a beer. The left one is like what you are seeing here is beer company, which is in Hopmeadow beer company, which is in Hartford County. If you look at the picture, like the entire manufacturing process, bottling, and customer service, consumption, everything happening in under one roof. The right side is like it's Budweiser's brewing company's northeastern facility. Just in a couple of pictures, we could able to show like the brewing capacity and bottling only. Because the moment it's become big, there are a lot of automation and other elements and guardrails, everything comes into the picture. That's what.
Did you get to take those yourself?
No.
Did you get to take those pictures?
No. This one mine, like not this one, like it's I got from Google. Okay. No. So when the company is really becoming big, it's becoming more complex. Like it's a more complexity comes into the fabric, like a data governance fabric and data protection thing. Why I'm saying that is like the company like is the couple of healthcare companies is in like is a Fortune 10, like they are like kind of like is next to Amazon and Walmart. They make so much revenue and also they touch like so many people's life. And when you go and look into the big companies, like they have a multiple line of business. If you go and look at the healthcare, like healthcare insurance is a major business. They may have like the payment card, like PayFlex or all those things, they will be having it. When it comes to the pharmacy, it's a pharmacy benefit, retail pharmacy, and specialty drugs, all those things, it will be there. Other services, primary health, senior health, like it's health hub and all those kind of a thing. And also they will have a retail. When you have like the different line of business, when you do the vertical integration, Department of Justice brings into the additional complexity. Hey, you cannot share certain data from one line of business to another line of business. Okay. So we have to secure the data much more strict than what HIPAA recommends. That's the reason we go and follow certain implementation. Couple of them is encryption, and another one is anonymization, which is de-identification. Many of the people in our industry think, hey, you encrypted the data, so it's a de-identified. I can go and use for any purpose. No, it is not, because if you encrypt a data, you can obviously decrypt and you can see who they are as. Yes, it's kind of like some thing. If you put a mask, it will make you as some other person. The moment you remove the mask, it's going to be the show your original face. That's what it is. And anonymity, like if you apply something, like it's, even though if you are trying to remove it, it's not going to show who you are. That's what anonymization is. Yeah. Just small comparison. Hey, what with respect to HIPAA, with respect to encrypted data, where I can use it's mostly for internal use and less restrictive use cases. I cannot share this encrypted data to my partners, data partners, for any reason, because it's either encrypted and still it's easily identifiable. The manner how we implemented the encryption. When it's come to the anonymization, we will strip off all the personal information, and yes, this information can be shared for further analysis, like it's for research or any other purpose. This is an example, like, hey, how a data look alike in the encrypted way and also anonymous way. If you see the like the plain text value, the second column, if you do encrypt or mask, it will produce a different kind of output. Like it's not a human readable, like you cannot make any sense. But like each and every value, name, address, zip code, and unique IDs, it will be encrypted, and it will produce the output, the ciphertext, without compromising any referential integrity. What I mean is, if I encrypt one data, anywhere at any time, it's going to produce the same kind of output. That's what is the goal of our encryption is. We use something called like a format preserving encryption using FF1 algorithm, which is patented and used by the Voltage. That's what we use. The next one is comes to the like some date of birth or like age and service date. Certain cases we won't encrypt the date of service, but we always mask age. The reason being is, if you encrypt, if you want to go and do analysis, like it's you have to decrypt all those data before you go and apply them any restrictive. So what it's going to take a lot of computation, and it's a lot of energy at any big data environment. So we mask it, and we will give a privileges of unmasking only to the certain people who deliberately need it. It's most likely it's to like data scientists, and it will not be given to the any data engineers or those things until absolutely it's necessary. In other hand, if you come and look at the anonymous data, and first thing like is we will be strip off the address name, but in the place we will be creating a tokenization. I will go and talk about the tokenization later. And when it's come to the zip code, you can see like the 106105 it's become 06100. And like it's the other dates, it's everything, including the date of service, everything becoming stripping off like month and day, only it retains year. It's little bit like about how we implemented the internal of Voltage format preserving encryption, how we do. When we go and set up the Voltage, like it's we will assign a key for each and every line of business. So data encrypted by using one line of business cannot be compared with the other line of business data, which is encrypted by using another encryption key. So the same data encrypted outside of a one line of business it's not comparable until unless you go on decrypt and re-encrypt the same common key. The beauty about the format specific encryption is if I'm encrypting like the 10-digit string, like it's going to 10 character length string, it's going to the output going to be a 10 character a string only. Because of this, we no need to change any data model or no need to change our code to go and comply with this requirement. It can be implemented in RDBMS, it can be implemented in any big data, Hadoop, Hive, flat file. Even we implemented in GCP, BigQuery, and Dataproc, other third-party tool, business intelligence tool as well, like we implemented. So it can be implementable anywhere, wherever the data goes. For the next one is the de-identification. Like, hey, this is like very less protective de-identification. We call something like use format serving hashing. This also follows the same standard as like it's a format serving encryption. If it's encrypt 10-digit 10 character string, it's going to output 10 character string only. But it's like it's a one-way hashing, we cannot hash it back. This it will be used for only our internal purpose because this is less secure or like it's somehow easily crackable or easily go and identify one record individually and map it back. Because we can encrypt any person's we can hash any person's data and create a reference table and use it because it has a little bit of risk. So it does not use like it's other than internal purpose. Coming to the tokenization standard where like is which follows a safe harbor method. The earlier one is like the statistical reference method. So which has a little bit of risk of identifying. This one, a data token based one, it does not have such a risk, like it's almost close to zero. And HIPAA says we have to strip off certain information, first name, last name, and street address. If you see here, the left side is the plain text, the right side is like what our de-identified data. But when we de-identify, we will create a token by concatenating first name, last name, date of birth, and then gender. These three data, it will be concatenated and it will be a token generated by doing a one-way hashing. Internally, how it works, we use product called DataVent, which has a portal, its own portal. The portal it has like a site-specific salt and also site-specific encryption key. This tokenization is a two-step process. In the first step, it will do one-way hashing of by using a secure hash algorithm 256. By using this algorithm, it will do the one-way hashing. And then it's apply encryption by using a site-specific key. And once it encrypted, it will apply base 64 encoding, which will standardize the length of the output always to be a 44 character length object. Okay. This is how like we generate the token. This data, whatever the de-identification data, we can share legally, we can share with somebody like outside of our organization, even within our organization, to combine with like it's a multiple line of business data in a single place. Okay. Before that, we cannot do it. And now we'll go and look at the use case of, hey, if I want to share the data with somebody outside of my organization or outside of my line of business, how it can be done. When you do decided to share to some other line of business or any other party, first you need to establish the relation, and we need to agree upon a shared encryption key. for what it will be used, because whenever we create the tokenization, it was encrypted by using a site-specific encryption key. So that key is only belongs to the parent organization. If you want to share, what we have to do is, the first step, we have to decrypt the data by using our own parent site key, which will produce the output is like some hashed value, a secure hash 256 value. Once we have the value back, and it will be re-encrypted by using a shared key, so that it can be data transferred to our agreed partner. That's what the last step it will produce. Output is going to be a 44 character, doesn't matter like length of the source. So it's consistent. Once we produces, like it will go to our partner side, like the partner receives data, and they will be running operation called receive from. What it would happen, they would have a shared key, what like we agreed upon, we are using it. By using a shared key, they will decrypt the data and re-encrypt the hashed value by using them parent key. Then only they will have like it's a standardized token, and the standardized token can be compared with them existing data in the premises. Okay. This way, like this data can be shared not only the like internal line of business, and also like we can share with like a third parties and like our other data partners. We do use other data protection mechanism. It's called the column level restriction. If in any data warehouse like or any other database, like if you don't want to share certain columns, we will be using this. It's most of the time like it's provided by the software manufacturer itself. And the next one is a row level restriction, where we don't want to certain clients information we don't want to share, means we will put a restriction based upon the rules or like them security group or like them department where they are belongs to us. And the restriction it will be implemented. The third kind of a one, like which is like is a very trivial or like is a fundamental of like any data security. It's server-side encryption or at rest encryption. So all the server-side encryption and at rest encryption, it will be implemented by using a customer managed keys. That's a standard what followed. So these are the certain procedures what we follow secure our data. I'll stop here, and if you have any question, you can ask me. Yeah.
So I will start.
Actually, algorithm biases comes with the based upon the input data. Okay. It's most of the time negligence or like kind of training data what we use. To overcome that, like is our organization has special team to go and validate the data. Is it trained on proper data? It's a balanced data. It has all the inputs. Another thing is like it's in a healthcare industry, the language and race are like restricted of field. We cannot use these two field to go and predict like our analysis. So basically, it's fundamentally it's a block. Like it's if you go and need to look at the data, you need further clearance from our data governance and privacy office. It's not that easily available to feed it into the algorithm until unless it's specifically mentioned. So in that way, the language and race are not included in any of our analysis. Any other question? Thank you. Thank you, everyone. Thank you.